This is a video for AQA Further Pure Mathematics, Algebra and Graphs, Section 3.1. We're introducing the idea of conic sections and looking in particular at the parabola. Well, firstly, what do we mean by a conic section? Well, conic refers to a cone, of course, but not just the cone that you might be familiar with, but one which has got a reflection above it, so that it's what we call a double cone. Now these go off to infinity, so plus and minus infinity. So that's the idea of the cone, a double cone rather than just a single cone. The idea of a section is to slice the cone with a plane. So if you imagine this plane slicing through the cone here, and then considering what shape we get with the intersection of that plane and the surface of the cone. Now, to investigate that a little bit more easily, I've got a Geogebra file that I'm going to use. Well, this is the file, and you can see at the moment that the plane is cutting the cone parallel to the base of the cone, and the curve that we get is in fact a circle. Maybe not so easy to see that it's a circle from there, but if I turn so we're looking directly from above, you can see definitely that that shape is circular. And it doesn't actually matter at what position we put the plane, we can move it up and down and it remains a circle. So if we cut the cone parallel to the base of the cone, then the shape is a circle. I can change the angle of the cut, however, and if I move to there, then you can see that that circle is now elliptical in shape. Indeed, if I move to the top there, looking from above, you can see it's no longer a perfect circle, but more of an ellipse. And that's going to be the case as long as the angle of the cut is less than the slope of the cone itself. But if I move round so that we get to an angle which is equal to the angle of the cone, you see now that the curve that we get is no longer a closed curve. It doesn't matter how far I move this up and down, it's an open curve, so it's obviously different to the one that we had before. And this is in fact a parabola. So now we've got the angle of cut is parallel with the cone. I think if I move it to there, you can see that the angle of slope of the cone is the same as the angle of the plane that's cutting it. I can make this a bit steeper, and now we see that the plane cuts both the lower and the upper cone at the same time. So there are two branches. And this is a new curve. It looks very similar to the parabola, perhaps, or at least each branch looks similar to a parabola. However, it's different. It is in fact what's called a hyperbola. So for the conic sections then, we found the following. That if the angle of cut is parallel to the base of the cone, then the curve is a circle. If we increase it slightly so that it's less than the slope of the cone but not parallel to the base, then that is an ellipse. When it's parallel to the slope of the cone, it produces what's called a parabola. And then finally, when we're steeper than the side of the cone, we've got a hyperbola. So these four curves, the circle, ellipse, parabola and hyperbola, are what are known collectively as the conic sections. You've probably already met the equation of the circle, and in the rest of this video I'm going to be looking at the parabola, and in later ones the ellipse and the hyperbola. So now let's go on to look at the equation of a parabola then. We draw a parabola on its side, as it were. You've actually met a parabola in the curve y equals x squared. But when we're talking about conic sections, we refer to the general parabola as being a curve which has equation y squared equals 4ax. So you can see that the shape is the same as y equals x squared, but it's been turned through 90 degrees. More correctly speaking, I suppose it's going to be a reflection. And this is our general curve y squared equals 4ax. For different values of a, then the curve will simply have different slopes to its sides. All of them will pass through the origin. So if x is equal to 0, then y squared must be 0 and y is 0. So all of the parabolas pass through the origin. As a increases, then the curve gets wider, and as a is less, it gets narrower, as it were. So for example, if I have a value of a equal to 1, then that's the curve which is shown, y squared equals 4x. If we had a equal to 2, then that would give us y squared is equal to 8x. So for a equal to 2, y squared is equal to 8x, and we can consider some other points. So that then when x is equal to 2, that would give us y squared is equal to 16, so we'd have y is equal to 4. So we'd have a curve coming through 4 or negative 4. And you can see therefore that the curve is going to be something like this, certainly going through the point 2, 4 there. The next so going like that, and coming downwards similarly is just a reflection of the upper half. If I had a was equal to a half, so we had y squared is equal to then 2x, then when x is equal to 2, y squared would be equal to 4, so y would be 2 or negative 2. And you can see then that new curve is going to be rather narrower, this sort of fashion. But all of them passing through the origin. So there we have a equal to a half, a equal to 1, a equal to 2. Now you might like to consider what happens if we had a value of a which was negative. Is that possible? And of course, yes it is, but if a is negative, then we need x to be negative to give us y squared as a positive number. So as long as we have then values of x which are negative, then we'll see that the graph exists in the negative portion of the axis. So it would be over in this direction for negative a. Right, that's the end of this particular video, where we've considered the equation of the parabola, y squared equals 4ax. In the next one we'll be looking at the ellipse, which is one of the other conic sections.